450 degrees centigrade. That is the temperature of the surface of Venus due to huge greenhouse warming caused mainly by the massive carbon dioxide atmosphere. Higher up in the atmosphere, one finds cooler temperatures, similar to those on Earth. But how variable are these temperatures, and does this give us clues about atmospheric circulation? Scientists knew very little about how atmospheric temperatures on Venus varied until recently.
As you know, on Venus we have a very hot temperature on the ground. We have almost 450 degrees Celsius, and from this point on, if you go upwards, you see that it's getting colder. So the temperature is decreasing up to a certain point, which is called here the tropopause. And the same is true on Earth. You also have a warm surface on Earth, and then it's decreasing. But the difference is the atmosphere above. On Earth you have an increasing temperature above because you have ozone and you have a stratosphere. On Venus, you can see that you have a complete change of the behavior when you go upwards. So, as you can see, this is a particularly interesting region on Venus because you have, on the one side, you have this more or less boring-looking troposphere, and you have this interesting region above, and you have the clouds in this region, and therefore it's exactly the region we are interested in. We're using the subsystem, the radio subsystem of the spacecraft. Each spacecraft is equipped with such a radio link. This is done just to communicate with the spacecraft here on ground. And you can also dump data down to the ground with this. So you have just a single radio frequency coming from the spacecraft, going down here on Earth, and it's received here on one of the large antenna dishes here from NASA and ESA. And we are doing this in a so-called Earth occultation geometry. This means Venus Express is going behind Venus as seen from the Earth. And when it's doing this, this radio link has to propagate first to the ionosphere, and later on it goes through the atmosphere. And this leads to a certain bending of this radio link. And from this change in frequency, we can then calculate how dense is the atmosphere of Venus. And then it's quite easy to say something about the pressure and the temperature on Venus. So one of the interesting things we see in these data is a huge number of small-scale waves we see above the tropopause. It's not really clear what excites these waves. They are probably generated in this cloud layer because this cloud layer is almost adiabatic. It means it's convective. This means that the air particles can move up and down, and they can probably also push the atmosphere above and below. And this might excite this atmosphere to move up and down, and then you have these waves. But there are also indications that some waves might also be generated by some topographic features here, by some large mountains that you see here on Venus. For example, we see many of these waves above this large mountain range, Terra, in the high northern latitudes. The very interesting thing here is that how is it possible that waves generated here on ground can propagate to these altitudes, which are 65 kilometers or even higher. On Venus Express, it's also seen, for example, by the VMC camera. And then there's a nice paper from Arianna Picciali, which shows here that they also see a lot of these waves over Terra in the high northern polar latitudes.
In the heart of the Alps, at 2,250 meters altitude, Arianna is going to continue her study of the atmospheric temperatures on Venus using one of the most powerful interferometers in the Northern Hemisphere, NOEMA.
The view is really fantastic. We are surrounded by the mountains and we are quite isolated.
By simultaneously using 6 antennae, Noema can achieve some of the performance of a single dish 760 meters in diameter.
And when we arrived this morning, the sky was wonderful and very blue, but for the moment, a big storm started. So we are surrounded by snow and huge wind speeds of more than 100 meters per second, kilometers in fact, per hour sometimes. So it's really, really high winds. So for the moment, we don't know if we will be able to observe. For us, this observation with Noema are extremely important because we have already observed Venus atmosphere in the past with Venus Express, but Venus Express died last year. So since more than 1 year, we don't have really observation on Venus, and the only way to observe Venus is the ground-based telescopes. With Noema, we can observe in the zoom millimeter, which gives us the possibility to sound the mesosphere of Venus, which is a region very interesting because it's considered a transition region between the lower atmosphere and the upper atmosphere. It is characterized by very strong winds, a bit more like the one that we observe here. It's characterized by a temperature that changes a lot from one day to another. And so the idea is to arrive at a sort of climatology. So we need to understand why this planet evolved in such an extreme ways compared to her sister, the Earth. So I'm very excited about this measurement, and I really cross my fingers that tomorrow the weather will be good.
Space research takes time and incredible engineering, but also sometimes a little bit of luck. As the weather improves, the giant instrument is finally able to observe the atmosphere of Venus. It will take Ariana many weeks to process all the data. The results will be used to build up a more complete understanding of the atmosphere on Venus by combining them with those obtained by other members of the EuroVenus consortium. Meanwhile, and back in Cologne, another ground-based technique is being used, studying light emitted by carbon dioxide high in the atmosphere of Venus at a very specific frequency.
So to see this spatial peak, we need an instrument with a really high resolution, and therefore we need a special principle, so a special technique, and this technique is called heterodyne, and therefore we only have 2 instruments worldwide, and the one is this one you see behind me. It's the one developed here at the University of Cologne, and in the instrument we overlap our signal coming from Venus, so the light coming from Venus, with another signal we really know, we really can control, and then we measure the difference between both signals, and in the difference we can see this peak. We just look at a really small frequency range, and then we can see the peak, and we can measure the peak, and then we can get the temperature by using a really famous equation here in physics. So it's the Doppler equation we use, and the Doppler equation gives us the temperature in the atmosphere. So we measure temperatures in a specific altitude of Venus atmosphere, so it's about 110 kilometers from the surface of Venus. And if we measure close to the closest point of the sun in the atmosphere, we measure temperatures about 0 degrees. And if we move away from the closest point from the sun towards the morning or towards the evening, we see the temperature is getting lower to about minus 80 degrees. And if we compare our temperatures with other instruments, for example, with the SWIR experiment on board on Venus Express, which was orbiting Venus for many years, and we compare with the results from the Belgian team, we see that they measure nearly the same temperatures and the same structure we measure, and that's really good because then we know that their results and our results are showing us the right temperature in the Venus atmosphere.
To measure the temperature of the upper reaches of the atmosphere on Venus, we need to get even closer. This is what the Belgian EuroVenus team did by placing on Venus Express an instrument they built called SWIR.
So that's actually a copy of the SWIR instrument, which was flying on board Venus Express. So what we were doing actually, the principle of the measurement is quite simple to understand. We see it every day when we look at the sun at sunset or sunrise. Actually, we were looking at the sun while it was setting or rising on the planet, and but from the spacecraft, not from the ground. And the principle of the measurement is that we first measure spectra of the sun while we look at the sun outside of the atmosphere, and then from the spacecraft we were seeing the sun setting, so we were measuring at different altitudes, and from these spectra we could deduce the composition of the atmosphere of Venus. From the composition there are some laws that allowed us to, physical laws that allowed us to retrieve the temperature profiles. So that instrument is very powerful. We have a lot of measurements, but it has one limitation, which is that we can only measure at the terminator, which is called the terminator. So the thin limit between day and night. So it's either 6 p.m. local time or 6 a.m. local time. These measurements were quite interesting. They showed two main things, actually. The first one, which is the most important, is the very, very large variability that we observed amongst all our temperature profiles. When you look at the temperature profiles on Earth, we observe variations, as we observe here on ground. One day it can be 10 degrees, the next day it can be 20 degrees. On Venus, the temperature differences that we were observing from one day to another were varying up to 50 to 60 Kelvin, which is very, very large. The second one is something that we did not expect at all, which is a very, very cold layer that we observed at an altitude of about 120, 130 kilometers. Actually, the temperature is dropping at these altitudes at the level of the terminator, so at the limit between day and night, down to temperatures of 80, 90, 100 Kelvin, which means minus 170, minus 180 degrees Celsius. It's almost the temperature, it's very close to the temperature of solidification of CO2. So we did not observe it, but we could have CO2 ice actually at these regions. And it's quite amazing because we know that Venus is very warm, the warmest planet of the solar system, which has an atmosphere, not talking about Mercury. And there we observe on that same planet one of the coldest temperatures amongst Venus, Mars, and the Earth. So this is quite an incredible result that we had. We did some investigation in order to understand what were the physical reason of this temperature. And actually it is due to that same CO2, so the CO2 that is heating up the lower parts of the atmosphere at this altitude has some properties that makes it cool down the atmosphere. Actually, it's mostly due to the collision of the CO2 molecules with the atomic oxygen molecules, which de-excitate the molecules and actually pump up the heat and cools down the atmosphere. And that's probably the reason why we don't have that effect on Mars or on the Earth, because we do not have so high concentrations at these altitudes of CO2 and oxygen. So that's probably the main reason of why we have these temperatures.
From 450 degrees centigrade at the surface to minus 180 degrees centigrade at 120 kilometers altitude, planet Venus really is a planet of extremes. For Silvia, Ariana, Pia and Arno, understanding these extreme temperatures is a way to understand what determines climate not just on Venus, but on terrestrial planets everywhere.